Well, I guess we've talked about all of these. In terms of what we talked about last time, we talked at least about two of these. Monday was this. Wednesday was gradually varying flows, which we were talking about now. Today, we'll ultimately talk about rapidly varying flows, but maybe it's worthwhile just recapping exactly the characteristics that we talked about before. And if you remember, we talked about flows which can be defined in terms of the gradients of the different components. And certainly we called the gradient of the bed S0. We called the gradient of the energy grade line. Greetings. S sub F, and the gradient of the water as SW. We had the depths of these flows as upstream and downstream. Y upstream, or Y1 and Y2. We had the velocities of these individual components, V1 squared over 2g, etc. And the expression that we had that came out of it that was useful for us, we defined as being written in terms of Bernoulli, and we wrote it specifically as, instead of v squared over 2g, we change it to being a volumetric, a flow rate per unit width squared is equal to y2 plus, I guess that's not right, plus q squared over 2g y2 plus sf minus s0 times the length. And the length of flow is this, kind of in the x direction. Doesn't matter whether you do it horizontally or in the direction of the bed, because it's a shallow sloping bed. And we made the point. So this is Bernoulli, right? So this is P over gamma. So it's the pressure at this particular point here. It's the pressure head. This is the velocity squared over 2g term. There would be a z term here, right? Z1. But this term here is captured in the slope of the bed between the upstream and downstream. So we don't have this Z1 term. And so this is what we've called the upstream energy, specific energy, E1, which is equal to E2 plus this term here. And so these individual portions, in terms of what we talked about in Bernoulli, this is, well, this term here is essentially Z1 minus Z2. So it's the slope of the bed divided by L. So S0 is just this term here. So if you multiply by L, it cancels out. And the other term is the slope of the energy grade line. And so this actually is equivalent to the head loss. So in other words, if you look at the head loss and going from upstream to downstream, this is it. So this expression that we have is absolutely no different from, it's cold on the ears, isn't it? It's cold on the ears. And so this term is no different from Bernoulli, but with things cast in a slightly different way. And I guess the innovation for us was that we're talking about an open channel that looks like this, where this is the perimeter. We have an area underneath the depth of flow. So I guess this would be the area. The hydraulic radius, which we're not using right now, is equal to the area of the perimeter. But I guess more importantly, in this particular figure, we choose a width which is equal to 1 meter, or 1 foot, I guess, in English units. So this is 1 meter. And we look at the flow going into it, which is Q, which is just equal to the average velocity multiplied by the depth multiplied by 1 meter. So this is the depth, y. So that's it. And so we classify it in terms of this expression, which we use. And this is the term that we choose to be able to characterize flow in. And we talked about these specific energy diagrams. And so the goal is to be able to draw a diagram which is in terms of the depth of flow and the energy, which is y plus q squared over 2gy. Maybe y squared, actually. Yes, y squared. And y occurs, of course, in both sides of this. This is depth. And we have one kind of bounding curve, which is y equals e, which is useful to define. And we have, so if you go through this and you just substitute into this equation a given flow rate, which you have for your stream, and choose all the values of y from 0 up to some number, then you get a curve that looks like this. Not very, a bit wobbly, and like this. And we said last time that for any given value of energy that you have, so E equals constant, you could have a flow regime which would be this, or this, but not this, because this is a negative depth, which doesn't make any sense. And in terms of what this means is if you drew a line across here like this, and if you drew a line across here like this, then this could represent a weir, if you liked. This is the essence of what we're doing. This is the water level in the upstream part of the weir. Water's flowing underneath here, and it's at some, I guess this depth should be exactly at this 0 height here. So this is the base of flow. So in this particular case, the gate that we have that's in the way of this is causing this water to flow underneath the weir. It starts off at this magnitude here, which we call subcritical. And we call this supercritical. The velocity, sorry, the flow rates Q are equivalent because of the way we've done this, but the velocities aren't. So the velocity here is high. Sorry, other way around, right? Velocity here is low, and the velocity here is high. Q's are the same, but the velocities are different. And so that allows us to see why we can get these apparently two different flows in this case. In this case, it's enforced by the fact that we have this barrier here that makes it do that. And it's obvious that it's constrained to do that. And we can define a critical flow. So subcritical flow would be the Froude number is less than 1. This critical nose, I guess, would be a Froude number equal 1. A lot of stuff going on this diagram. And this would be a Froude number greater than 1. And we'll remember, I guess, that the Froude number, I'm never sure how to pronounce it, is the flow velocity in the system divided by gravity times the depth. And you'll remember that this is the speed of the wave, wave speed, celerity wave speed, divided by the speed at which the flow is going. And I guess what that means is that the Froude number is less than 1. We did this picture of dropping a drop in the water. Then it means that the ripples that come out from that, because the water is flowing at some velocity Vs, a Froude number equal to 1 is this critical one, which is these concentric circles are all centered on this upstream part where you drop the bead of water in as you're spitting off the bridge. I don't know if everyone's done that. Doesn't everyone spit in the water from a river to see your own ripples? And a Froude number greater than 1, which would be this. And we explained that kind of in the idea of a Mach cone, just like a plane going through the air. That because the plane is traveling faster than the speed of sound, in this case the speed of the celerity wave in water, the energy can't get away. So I guess the analog for a plane in water would be a boat. So a boat plows through this. This is the wake of the boat. The bow wake can't get the energy away from the boat, and therefore it takes much more effort to put the boat or the ship through the water. And I suppose ultimately, you could imagine that this wave goes past you. The reason that we hear a sonic boom is that if you're standing some distance away from the plane as it goes through the air, then ultimately as this thing migrates to your left, then this wave will hit this. So this is the same as a sound wave. Bang. All of a sudden you get all the sound that's coming out of this plane flying hitting you at one time, which is a sonic boom. Or you get hit by the wake if you're in your kayak and you capsize. But if you're standing here, then for a case where it's going less than the speed of sound or less than the celerity wave, then you get hit slowly by the first wave, then the second wave, and the third wave. Here you get all the energy hitting you at once. When, as this moves further to the left, then it's the same as you moving closer to this, so that when it hits you here, you hear it all at once. So that's kind of where this fits into everything. So that's kind of where we deal with gradually varying flows. And I'm not sure, we have some examples that we didn't do last time, but it's probably worthwhile doing them, but not doing them mathematically. So the wonderful thing about this way of looking at things is that you can do things graphically. It fits onto this curve. And so there's a lot of math in this, and I don't want to touch the math at all. And it's an example from the book that talks about what this would look like for a real condition. Of course, the weir is a real condition, but it looks kind of obvious. You stop the flow, you have upstream flow which is quite high, downstream flow which is forced to be low, and therefore you can see exactly why the flow works that way. But what if you have what seems a bit incongruous, an upstream flow which is going at some flow rate, Q is equal to something, and which would be Q1, and by definition Q2 is the same. But as you go downstream, instead of having a horizontal bed that is at constant height, you have some ramp in the flow. And what would you expect to get from that? Well, you could take this value of Q. You know that we can define a value of energy, which is just equal to the height plus Q squared over 2 times gravity times y squared. We know the value of this flow rate, say, for this example. You could take the value for the depth of flow as being equal to y equals 0 to 2.5 feet. And the reason for 2.5 feet is it covers this 2.3 and something else. And if you substitute the value of y into this expression for that, you get an energy curve, which is this curve here. So Q is constant, and it has this. It obviously has the other part that goes up here, but we don't care about that. And so we could look at this system. We know that upstream we're at 2.3 feet. And so if we go across here at 2.3 feet to this point here, we absolutely define what the energy would be at this point, which turns out to be 2.4. It's in units of feet, specific energy. It's in units of length. And so this is the energy which is present within our system. And we could also get it by just putting 2.3 feet into this equation, and we get energy out of it. But what this says is that if we're subcritical at this point here, then this is the point where we are present at. And we could examine whether we could also be in this regime. Turns out we can't. But we could also look at what the height of the flow should be as we get to this downstream point here. And so the downstream point here is that the energy here has changed by, so delta E equals 0.5 feet. So this is the value of energy we started off at, which is 2.4 feet, which is just the reading that comes from going across from here and down. We know that downstream we're at an energy which is 0.5 feet less, 2.4 going to 1.9. And so now we're on this line here. And so we know that at this downstream location where we are here, we're either at this point on the curve or this point on the curve, or I guess the negative one, which we know we aren't. And so we have to figure out which one of these we're at. And so the reality is that going from here to here, we have to go through this nose. And so that means that we have to go from subcritical to supercritical, which would be this one here, to get there. And we can't do that because it means that we've got to have gone through this particular point here, because we can only go down this line and across to this point. And so the flow that we have downstream of this flow we know has to be not at supercritical, but it has to be also subcritical. And so we have to be, well, never mind about supercritical and subcritical. We have to be at this point because we haven't gone through this nose here. And of course we know that this nose is where the Froude number happens to be equal to 1. Critical, I guess. Not supercritical, not subcritical, but critical. And so so that we know then that the depth of flow that we're at would be at this point here. And so we can go to this point here, and it turns out to be, the math is all here, and I don't know if I can see what it is. I don't know what it is. This is all explaining this, 2.22 feet. So I guess this point here turns out to be, no, must be something different, right? 2.22 feet is the height, but 2.22 feet minus 0.5, I guess is 1.72. So I guess this is 1.72, just from looking at those numbers. So that's what it has to be. So this has to be the free surface if you just have a ramp, but nothing else. If you want to get to this other point, then you have to go through a place where the flow will be just right, the Goldilocks zone. So that is that you need a place that has a bump in it, and this bump has to be high enough to force it to go through this point here. So I guess the height of the bump has to be this length here. So instead of being 0.5, which would be to this point, it has to be 0.5 plus another magnitude. So I guess just by looking at the ordinates here, this bump has to be 2.4 feet high minus 1.51, which is equal to 0.89 feet. So this bump here has to be exactly this 0.89 feet. And if you do have it at 0.89 feet, then you get to start off here upstream at this point here. You get to be flowing downstream through to this point here, which is directly above the bump. And so you'll go down the specific energy curve exactly to this point here. And then I guess the flow gets to choose at this point where it goes. And so you come back down here, you're at this depth. Now the bump is receding back to this value here. So I suppose you could go up here, back to this point here, or you could go down to this point here. You have a choice. The water has a choice. It knows its own mind. And I don't know exactly how to choose between those, but it has those two possibilities. So the only chance for you to get to this lower depth downstream, which would be this height here, is if you go across a bump. And if you go across a bump, it could choose to be subcritical by going back up to this point here, or supercritical by going to this point here. And I guess you probably don't know which one it's going to choose. I'm not sure how you choose between them, but you certainly know that if you don't have this bump to get you to this nose here, then you can't get to this point because you can't go through this thing. So that's the graphical explanation. I think, hopefully, well, I think that makes sense. I do that just because I don't want to go through 2 pages of calculations, which is what this kind of derivation is here. And it's not necessary. So this derivation is just making exactly that point. Yeah, and so we don't need to do that. And so I guess this figure kind of explains it, maybe a bit better. And that is that if you have, this is the geometry that we had. We had subcritical flow upstream. We start off at this point. If we just have a ramp, and that ramp is only enough to get us an energy change, which is this amount, we can only ever end up at this point, which means that the subcritical flow downstream from the subcritical flow upstream hasn't gone through this transition to get to this point, and so it can only be, it's a lower depth of flow, but it's still subcritical. It's still, both numbers are Froude numbers less than 1. If we have the ramp that's going downstream, then we can start off subcritical. We can go from this point subcritical through this ramp because it takes us directly to this point on the nose here. And then we can choose to either keep on going to this point here, which would be a lower depth of flow, or we could potentially go back to this point here as we go downstream to this elevation because the ramp's receding, right? We're going back down this height here, which would be this height here. And we'd end up either at this point and this point. And let's say we have this point here. This is a flow velocity, even though the Q values are constant for everywhere on this curve, lowercase q. So Q equals constant. Velocity is not constant, and hence the Froude number is not constant. And therefore, we could be subcritical going to supercritical because we go from a Froude number less than 1 to a Froude number greater than 1 at this point. And the other possibility, which I didn't go through, is that we could have a flow upstream, which is supercritical, in which case we would be at this point here, a very shallow flow. And now when we add the height, the 0.5 feet for this ramp, that's the same as changing the energy by this amount of 0.5 feet. And so we go to a flow which is still supercritical, right? It's still, this is a demarcation. This is a Froude number equal to 1. This is a Froude number greater than 1 for everything below this line. Everything here is supercritical. Everything here is subcritical. And so even though we remain being supercritical upstream and supercritical downstream, the depth of flow has gone up. This value here, not very well drawn, this value of depth that goes through here is higher than the value of depth that goes through here. And so this difference here is the same as this exaggerated difference here. So that's kind of the idea. So I think it's kind of interesting that you get to play with these things. And it kind of explains the reasons that you get the behavior that we kind of alluded to, that I'll show again and repeat. This is a big spring coming out of south of the Alps, north of Marseille in France, from I guess 8 years ago, in November about. And it's a beautiful limestone stream. The Alps are limestone largely. And it shows this transition from a nice flow that's very placid, looks kind of laminar, but you see these boils in it. It's still turbulent based on what we've said about Reynolds numbers in rivers. And it goes from being this placid flow that's still turbulent upstream to this much more turbulent flow as you get downstream. And I think here, occasioned either by the structures, certainly it's falling, so it's not a constant level flow, but possibly the width of the flow as it goes downstream is actually reduced. So if the width of flow is constricted, then the value of the Q, lowercase q, is increased because it's being forced to go through a narrower distance. And actually, can you see it here? I can't see it. There are actually slalom gates hanging in this section. And so it's the idea that you can actually get these behaviors to occur. So before we said it was a weir, upstream and downstream was enforced by this surface water structure, above water structure. Here we can get the same behaviors by having subsurface structures also causing the same thing. The other thing that we're talking about, and I guess we'll show this again, we showed it many times, is this behavior. So that kind of what we talked about in terms of energy is the idea that we can define this specific energy, this uppercase E, between upstream and downstream, and we can account for behaviors as we go from upstream to downstream. We can do things with weirs that force the flow to occur in such ways. We can do things by ramping up the base of the flow to make it perform subcritical to supercritical gymnastics, if you like. But we can also get those things in rapidly varying flows, which are always supercritical upstream. So a shallow flow upstream, as you see here, that's going into a different flow regime downstream. We know that certainly if it's upstream and supercritical, the downstream could either be supercritical or subcritical, depending on the conditions. And the question is, how do we deal with these so-called rapidly varying flows? And I guess the rapidly varying part, so we have these three classifications. Uniform flows, where the depth of the flow is the same as the slope of the bed of the channel. And that's the Manning formula, or the Chesy formula, which is just this recipe, which is your next Friday entertainment, I guess. We have gradually varying flows, which we use this energy, uppercase E, equation for, which is really just a way of rewriting Bernoulli equation to define the behavior. And the idea is that the flow from upstream has an energy loss within this behavior, but it's only a relatively small energy loss. And for rapidly varying flows, it means that it goes from a regime upstream to a regime downstream over a shrinking length, a length which is very short compared to the length of the river. And that's essentially what we're seeing here, which is a hydraulic jump. And so if we want to be able to deal with this energy loss that occurs between upstream flow and downstream flow, it's because it doesn't really represent itself as a one-dimensional flow anymore. So Bernoulli, we know, is a streamline. Upstream has a behavior, downstream has a behavior, and we're only characterizing it by one dimension. Yes, Tom Cruise flying for some reason. I don't want to do that. This is, what's it called? Top Gun, isn't it, right? The movie. I didn't want to do that. Well, actually, I have a different movie which does hydraulic jumps, so I could switch to that rather than find out where I was. One of these days, I'll work out how to rewind it. This is doing it in the lab. And I'll have this maybe playing in the background with the sound off. Yeah, fine. So I'll talk. And so the essence of this is that we have a weir that's causing this supercritical flow just at the tip of the weir, which I guess, if you can see my pointer is right here. It's coming under this weir. This is the upstream water level. And it's, for some reason, I think going under a second weir at the same level, but then it's going to a different flow as it goes downstream. So the question is, why does it do that? And it turns out that we could use Bernoulli, but it's not very convenient to do that because we don't know exactly what the energy loss is at this point where it goes from upstream to downstream, because it's not really a one-dimensional flow anymore. If you look at the flow, you see these eddies that are turning back on themselves, and a one-dimensional flow is one flow that's going from upstream and monotonically moving downstream instead of going downstream and then turning back on itself. So it turns that a one-dimensional approximation in terms of that isn't very useful for the things that we're trying to do. And so very briefly, I want to kind of address rapidly varying flows. And I won't dwell on it other than to say that what we could do is we could take a geometry that looks like this, which we've seen before, and in a couple of minutes make the case that this is the energy loss that we want to characterize in our system. And the problem is that as we go from upstream to downstream, we've always been used to being able to take a section across this and always being able to say that the volumetric flow rate across this section is the same. So we've always been able to say that Q is equal to, I guess, YV times width, right? For volumetric flow, it's this. If it's mass flow rate, we just multiply both sides by density. Don't need to do that. And so if you take a section on any one of these parts for Bernoulli, the requirement is that Q equals constant. But if you have flow going down here and turning back on itself in an eddy, which is kind of what you have in a hydraulic jump, then all of a sudden this really isn't doing it for you because it's not really a one-dimensional flow. So it turns out that one way to get around that, and the fact that we don't really know what this head loss is, because it's not due to these viscous properties on the bottom of the bed, but it's due to the energy that's mixed up in this churning of the water by the vortices that are present here. So it turns out that it's more convenient for us to write the equation in terms of momentum, which is kind of Bernoulli's equation, but not quite, because the momentum is basically F equals ma, right? And so this, I guess, would be the mass rate, and this would be velocity. And of course, if you write that out as rate of change of mass times velocity, then rate of change of velocity is acceleration, right? Which is what this is. This shouldn't be A, this should be A, right? What we've called acceleration. And so this is just F equals ma. And so if you do this balance, I won't go through the derivation, you end up with a momentum equation. So this is mv, m dot v is rate of change of momentum. Momentum's mv, right? And so we end up with a momentum equation, which actually looks a bit similar to something we've already had, right? This is the energy equation. We've multiplied this by the depth squared and the depth squared, so that this term here becomes, if you remember, Q squared, lowercase q, right? This is the upstream energy, E1. This is the downstream energy, E2. And the problem is we don't really know what this head loss is. It's not very easy for us to define. If we write the balance, the force balance in the system in terms of momentum, then it looks kind of similar. It has it says a y squared term instead of a y term on the downstream over 2. And it turns out that we can do exactly the same as this as we can with the energy equation. So we could write energy, so we could draw a graph that looks like momentum as a function of depth, whereas what we did before, we wrote energy, drew energy as a function of depth. And so our equation was what? Y equals E, not our equation, but our graph looked like our nose. This graph looks to be kind of the same. And if we do that, lo and behold, then we know that if we take a place upstream and we take a place downstream, we know that momentum is conserved. And so m upstream is equal to m downstream, which is equal to m. And so on this diagram, for constant flow rate per unit width, we can directly go up on this graph. And if we know what the behavior is upstream, which is supercritical, then by definition we know exactly what the behavior is downstream, which has to be, in this case, subcritical. And we could do it on the energy diagram just as well, but we need to know what the head loss is in the system to be able to do that. And because this head loss is due just to the swirling of the water in hydraulic jump, it's not very easy for us to figure out exactly what H sub L is. And so if we do it in terms of momentum, we can do it much more easily. So that's the hydraulic jump story. And so again, there's a ton of math that comes with this. I won't bore you with this, but that math allows you to define what the ratio between the upstream depth and the downstream depth should be, purely as a function of this Froude number. So we can play around with the momentum equation, do a whole bunch of things. I won't bore you with it, but it allows us to say exactly what this ratio of these two depths, the upstream depth y1 and the downstream depth y2, should be. And it's purely as a function, as you can see from this relationship, as a function of the Froude number. And so I guess we remember that if we're looking at these flows, if you look at Reynolds number versus either, I think it's 1 over Manning's coefficient or whatever, then we have this behavior here. And so this is a Reynolds number of 500 if it's defined in terms of hydraulic radius. And we said that we only did one calculation, but we said that we're always in the regime that's on the right-hand side of this. We're always in the turbulent regime. So clearly, Reynolds number isn't very useful for us to classify the flow regime, which when we talked about flow around objects, you'll remember that a laminar flow regime was this creeping flow where viscosity is important, and a turbulent regime is where you get this flow where you get these vortices breaking off the back. So a different flow regime in this. Not very useful for us for these open channel flows because we always think we're on the right-hand side of this transition. So the flow is always turbulent, so that doesn't say anything about the behavior. But what does make the difference in this is the Froude number. So the thing that influences the topology, or the topography, I guess, topography of flow is the Froude number. And again, I won't say anything other than that. Then if you look at these charts, this is out of Munson. If you have the book, then great. If you don't, that's fine too. Then because this equation that we just looked at gives us the relative upstream to downstream depth ratio as a function of the Froude number, which is constant through the system, or it might be the upstream Froude number. Actually, it's not constant through the system because it changes, doesn't it, right? Changes from supercritical to subcritical. Then if it's equal to 1, then that's a critical flow, so it doesn't change. If it's greater than 1 but not very big, then you get these boils. A weak jump, a jump that's pulsing, I guess, is an oscillating jump, a stable big jump, and a rough jump. So I guess if you're a kayaker, you want to travel, want to go boating in Froude numbers which get progressively larger as you go down here. So instead of the Reynolds number indexing the behavior that we have, it's defined in terms of the Froude number. So that's it. Anyway, so that's all I have. So I didn't know what I was going to talk about our New Zealand trip, but I thought instead of doing that, I might just go back to. So that's all we're talking about. So you know already in terms of what's happening on next week in terms of the midterms. There's nothing on anything that we've talked about on Friday, today, or Wednesday. Everything is the stuff on Monday. So, and that's, I guess, defined in the material we've already talked about. And you know, I guess, the things that we've talked about. And so you'll have no problems, I don't think, with the stuff in the new week. But you remember, if you can remember that back, either at the end of day 1 of week 1, or the end of or within day 2 of week 1, we talked about the kinds of things that we would be able to address. So now these things might make more sense to you. I'm not sure that the natural processes are so important, but we've talked about all of these things. And so now, other than knowing at that time, perhaps understanding just what the concepts are, now you can do something about it. Indeed, you've done calculations on some of these things. You know that you can use the stagnation point on a pitot tube to be able to calculate the pressure here relative to the pressure that you measure in the size of the tube, and from that extract the value of the velocity. You know that you can use drag coefficients on structures to be able to look at the forces that are applied, and therefore use that to be able to calculate the amount of work that's done on this. We've talked, certainly, I don't know if we talked in the videos that you saw this year, in terms of being able to calculate the work that you can get from one of these articulating offshore wave machines. We know that for work you have to have both force and displacement. And so if you have a buoy which is underwater with the waves going up above it, you have an oscillating force maybe applied on that thing, but you have no displacement. And so to be able to do work, you have to have the buoy sitting on the top of the water and traveling up and down with resistance from some kind of force for an anchor to be able to make energy from that. And so I guess in this particular case, you're doing work because you have an articulated joint that you're doing displacement against and applying force in this articulated joint, which must be here. We've talked about von Karman vortex streets, which are the vortices which are shed from a sphere or from the bridge deck as a function of the size of this bridge deck and also the velocity of flow. It only occurs at a very specific Reynolds number. And so if you're at that particular velocity, then it will give you a shedding of vortices from the top of the deck, then the bottom of the deck in alternation. And so that only happens at a particular velocity. And if that's the velocity the bridge is seeing, it will give a particular excitation to that bridge. And if that happens to be the guitar string frequency, the resonant frequency for that bridge, it will set it in motion and it will pull itself apart, as the Tacoma Narrows thing did. And we've talked about these now. We know why the dimples on a golf ball are useful, because on that coefficient of drag equation, as you go in the turbulent regime, it has a little drop. And that is where you use those dimples to make it go into this boundary flow regime early. So you have a very thin boundary layer flow. That boundary layer is so thin that it's actually quite efficient in allowing the flow to go past it. And if it's efficient in allowing the flow to go past it, there's less drag placed on the ball, and therefore the ball can go further. And if it goes into that regime at an earlier velocity, a lower velocity, when you strike it, then you have a better chance of having it go further. We've talked about surfing West Virginia. The balance is between gravity going down the surface of the wave, drag on the bottom of the boat against that wave, and I guess drag against air, if you're surfing, of the body going down the surface of on a sea wave. I guess in this particular case you're actually not traveling relative to the air that's around you, so it would only be the drag on the bottom of the boat that affects it. And I guess we talked about the idea that you'd have different kind of structures which could reduce drag, and perhaps also, I imagine that this hydrofoil also provides some lift to lift the boat out of the water. So I guess this is old school from the America's Cup, when you had monohull boats where this would lift the boat partly out of the water, and I suppose it would give you less of a wetted waterline for drag. But now, of course, with the catamarans and trimarans that you see for the America's Cup, you have these on the bottom of them, and they physically lift the whole hull out of the water so that the water level is only acting here, and there's a very small amount of drag here. And I guess the Sydney Olympics, can't remember when that was. Was it 2000? 2008 was Beijing. It might have been 2004 or 2000. Perhaps Greece was 2000. Didn't it go back to Athens in 2000? But anyway, for 1 year, and I think it was the Sydney Olympics, they allowed the swimmers, male and female, to wear these bodysuits. Now they just have cut-offs on the legs and arms. And the idea of these bodysuits was they made you much more efficient in the water. And I think the way that they make, one of the ways they make you more efficient is that they have fish-like scales on them that make the water cavitate that it goes past you. And so as it cavitates, it changes from water to being the dissolved vapor that's in the water. And those bubbles, the viscosity of water is something like 10 to the minus 3 Pascal seconds. You've seen that number many times. The viscosity of air is something like 10 to the minus 5 Pascal seconds. So 2 orders of magnitude lower viscosity. And it's that lower viscosity, I suppose, that makes these much more efficient in going through the water. So you get faster times on a given course. And of course, I don't know when the innovation came, but in the Olympic pools, they used to be just regular 6-foot deep pools like the natatorium pool that's on campus. But now the pools are at least 10 feet deep, or perhaps even deeper. And the idea is that the deeper the pool, the less, I guess, disturbance there is from the water hitting the bottom, and therefore you can get faster times in deeper pools as well. So all Olympic grade pools are now much deeper than they used to be. So that's it. So that's all we're doing. I was going to show this other video, but we're right on the limit. I guess I could ask you if you have any questions. You never have any questions. Do you have any questions today? So the other thing that I put together last night was a little PowerPoint presentation of this thing that we go on. I guess that's the wrong... Oh, no, that's the right thing. So we have this trip, I don't know, we have a dozen people signed up. So a lot of this thing, you know, we talked about fluid mechanics, but fluid mechanics also is a big thing in energy production. And so we have this trip to New Zealand to go and look at some energy sites. And we visit New Zealand's one thermal power generating station, about 1 gigabyte, which they're trying to phase out, but they had a big drought when we last visited in 2019. And so they didn't have enough water to run their hydroelectric plants so efficiently. And so thermal power, you see the river in the foreground. You have to use water to put through the turbines. The left-hand side happens to be a gas turbine that we know how that works, right? We talked in terms of the energy equation. You can write it in terms of Bernoulli, upstream or downstream, or you can write it in terms of enthalpy between upstream and downstream. And so we did an example where you used the enthalpy of flow to calculate the power that you get out of a generator. So it could be natural gas, what is the input in this particular case, or it could be water. We talked about flows. I wonder if I can get this to go. I can't. I'll have to shout against the... This is... Yeah, this is New Zealand's Bridal Veil Falls. I guess Yosemite in California has its own Bridal Veil Falls off Half Dome. Doesn't fall quite as far, but we did an example so you know you can write Bernoulli at the top and Bernoulli at the bottom to be able to see what the impact velocity is. We've done that as an example. We know that for wind energy, we know external flows allow us through drag and lift to calculate forces applied on structures. And so we know that those forces times the velocity of the structures give us work or power in the system. We know we get those same behaviors in hydroelectric dams. This happens to be one of the dams we visit. Upstream water level is something like this. It goes in a canal behind this powerhouse and then through some tubes, through some turbines in this turbine hole, and then into the old bed of the river, which is down here, and it goes downstream. And so we know how we can calculate the power from this because we know that HP is equal to power divided by mass flow rate times G, right? Our W dot formula. So we can just apply that. If we know the mass flow rate, we know the head drop between upstream and downstream. Immediately we can calculate power coming from that system. And we go to the second geothermal field in the world. First was Lardello in Italy. Second is Wairaki, and other ones in New Zealand, where they harvest hot water, they flash it to steam, and the generator looks exactly the same as the gas generator at Huntly Power Station that we looked at before, and generates power by turning the turbine blades, by taking a high enthalpy fluid and taking it to low enthalpy downstream. Not a combustion process, but just changing the enthalpy of the fluid in this particular case. Drilling rigs and Hooker Falls. Very famous falls that come out of Lake Taupo. There's a 4-meter fall, which is upstream of this. This is the tongue of the water that comes out of it, and then it goes downstream. It's constricted, and the flow regime changes from a moderately placid regime to a much more turbulent regime. And I guess we could imagine that that's influenced. It's not a hydraulic jump because it's going in the opposite direction, but it could be going from subcritical to supercritical flow because it looks like it's a lower level downstream. And New Zealand is a very low methane, low carbon country in terms of energy, but they do have offshore gas, and this is where their offshore gas fields comes on shore, and we know all about pipe flow and getting this. Interestingly enough, the carbon footprint for New Zealand, the largest part of it comes from agriculture, and the largest part of that agriculture is from animals farting, basically, right? Methane from animals. And so they have a very different problem for lots of developed economies. They're developed economies, but they're also an agrarian economy. And White Island, and I'll finish with this. And I just think this is an interesting thing to see. The left-hand figure is from a place called Greymouth, where there was a mine disaster. And so these are miners standing in this ring that's going around. And this ring is just driven by water. And so the water comes up at pressure. It's enough pressure to be able to lift that ring enough that when the water flows sideways, it provides enough drag on it to be able to turn it. It's a very, very interesting structure. And this other one is in Perth at the University of Western Australia, in Western Australia. And it's exactly the same thing. It happens to be a beautiful ball of rock. These little patterns you see are crinoids, which are fossils, probably some of the oldest fossil life on Earth. And this happens to be a sculpture that's been made of that. Again, the same idea. Water's coming up from below. There's enough water pressure to kind of elevate this big ball of rock slightly. And that when the water squirts out preferentially in one direction, as you're seeing here, then it makes the ball turn. And it's just self-turning. I think that's the last one. That's the last one. Yeah, that's it. So great. 1, 2, 3, 4, 5, 6. We lost one. Right. So that's all she wrote. And so hopefully this is useful to you in life. There's no doubt that what we talked about in fluid mechanics governs maybe very big parts of your professional life. connected with thermodynamics, the class that some of you, perhaps all of you, will go to now. But that's what controls, those control what goes on the planet. So try to bring it back to reality there.